Every day, developers write code that talks to databases. And every day, attackers look for one specific mistake that lets them hijack those conversations entirely. That mistake is called SQL injection, and it has been ranked the #1 or #2 most critical web vulnerability on the OWASP Top 10 for over 2 decades running. Understanding it is not optional for anyone building software that handles real user data. SQL injection is what happens when user input is allowed to change the structure of a database query. Instead of just supplying data, the attacker supplies code. And the database, which has no way to tell the difference, executes it faithfully. The application intended to run a query. The database ran a query. It just happens to be the attacker's query rather than the developer's intended one. The database was doing exactly what it was told. To understand why this happens, you need to understand how web applications communicate with databases. When you log into a site, the server constructs a SQL query using your username. Something like select star from users, here username equals whatever you typed, and password equals whatever you typed. If the developer builds that query by concatenating your input directly into a string with no processing, you can type anything you want into that field. The application has no idea whether your input is data or code. Neither does the database. Here is the classic example. The login form passes your username directly into a query string. You type admin, then a single quote, then 2 dashes. In SQL, 2 consecutive dashes begin a comment. Everything after them is ignored by the parser. The her clause becomes username equals admin, and the rest of the condition, including the entire password check, is now commented out. The database executes select star from users, here username equals admin. The password field is completely irrelevant. You are authenticated as admin without knowing the password. The server never detected anything unusual. That single quote is the pivot point. It closes the string literal the developer opened, and immediately gives the attacker the ability to append arbitrary new SQL syntax. Every variation of SQL injection is built on this same fundamental confusion between data and code. The database cannot distinguish between the developer's intended query structure and the structure the attacker has injected. To the database parser, both are syntactically valid SQL, because they are. This is not a bug in the database. It is a bug in the application's decision to trust user input as part of the query structure rather than treating it purely as opaque data. Union-based injection is the technique attackers use when they want to extract data from other tables in the database. The SQL union keyword joins the result sets of 2 select queries together. If an attacker can inject a union select after a legitimate query, they can append an entirely new query targeting any table they choose. They can pull every username, hashed password, email address, and session token from the user's table in a single HTTP request. If column counts and data types align, the results come back right alongside the normal application output, visible directly in the page itself. Blind SQL injection is used when the application does not display query results anywhere visible. Maybe the page just says success or failure. The attacker cannot see extracted data directly, but they can ask the database Boolean questions. Is the first character of the admin password greater than the ASCII value of the letter M? They observe whether the page behaves differently when the condition is true versus false. A different redirect, a different element count, a different HTTP status code. Binary search over all possible character values, fully automated with a tool like SkullMap, can recover an entire password hash in minutes. No visible data output is required anywhere in the response. Time-based blind injection is even more covert than Boolean blind. Instead of causing any visible difference in the application response at all, the attacker injects a conditional sleep command directly into the query. If the condition evaluates to true, the database pauses for 5 seconds before responding. If false, it responds immediately. The attacker reads the database 1 bit at a time using nothing but network response timing. The page content is completely identical either way. No changed output, no error message, nothing visible at all. There is no pattern for a web application firewall that only inspects response content to detect, and the attack leaves no obvious trace in standard application logs either. Error-based injection weaponizes the database engine's own diagnostic error reporting against it. Some database systems, when they encounter a malformed query, include fragments of the data that cause the error directly in the error message text that is returned. Attackers construct deliberately malformed queries that are designed to trigger these informative errors and carry the target data embedded in the error output itself. The error message becomes the data exfiltration channel. A single crafted request can retrieve the current database username, the database version string, the names of every table, or the contents of any specific row, encoded right inside a diagnostic error field. Second order injection is the most counterintuitive variant and the hardest for developers to reason about and review. The attacker does not inject into a query that executes immediately. Instead, they store a carefully crafted malicious value through a form or API endpoint that appears to handle the input safely. The value is written into the database and passes all the input checks and insertion time. Later, a completely different part of the application retrieves that stored value and uses it to construct a new query, operating on the assumption that data already in the database must be clean and safe. It does not escape or parameterize the value again. The injection fires at retrieval time, not at insertion time. The payload waited in the database for the right code path to activate it. The consequences of a successful SQL injection attack are severe and wide-ranging. An attacker with read access can extract every record in every table. User credentials including hashed or plaintext passwords, payment information, private messages, session tokens that allow full account impersonation without knowing any password at all. Write access means modifying account balances, planting backdoors, altering audit logs to cover tracks, or destroying data outright. In certain database configurations, particularly Microsoft SQL Server with XP_CM-shell enabled or MySQL with elevated file system permissions, SQL injection can be escalated all the way to executing operating system commands on the server itself. A database vulnerability becomes a full server compromise. The defense against SQL injection is well understood and has been documented for 20 years. Parameterized queries, also called prepared statements, are the correct primary solution. Instead of concatenating user input into a query string, you write the query with placeholder tokens and pass the user data as separate bound parameters. The database driver handles encoding the data so it can never be interpreted as SQL syntax regardless of what characters it contains. The structure of the query is locked before any user data is involved. An attacker who injects a single quote character gets a literal single quote stored in a string field, not a broken query boundary. Input validation adds a layer of defense in depth but cannot replace parameterization. If a field expects an integer identifier, reject any value that is not a valid integer before it reaches the database layer. If a field should contain only alphanumeric characters, reject punctuation at the API boundary. Validation rules have gaps and edge cases, which is exactly why they cannot be the sole defense. But they reduce the attack surface and surface programming errors early in the request lifecycle, before data ever reaches a query. Object relational mappers and stored procedures provide structural separation between query logic and data when used correctly. Modern ORMs, like Django ORM, Active Record, and Hibernate parameterize queries by default. Developers get SQL injection safety without thinking about it explicitly because the correct behavior is also the easiest and most natural behavior. This is why applications built on modern frameworks are dramatically more resistant to this attack class than raw string concatenation code from the early 2000s. The ecosystem made the right choice, the path of least resistance. The principle of least privilege limits the damage when an injection does succeed. The database account your web application uses should have only the permissions it needs for its specific tasks. A read-only account cannot drop tables. An account scoped to one schema cannot read payment records in another. When an attacker exploits a SQL injection vulnerability, they inherit the privileges of the compromised account. Reducing those privileges directly reduces the blast radius of the attack. Defense in depth means that no single vulnerability should be able to compromise the entire system. Web application firewalls can detect and block many common SQL injection patterns by matching known attack signatures. They are a useful additional layer, but not a substitute for parameterized queries in the application code. Skilled attackers use comment injection, encoding variations, whitespace manipulation, and database-specific syntax specifically to evade WAF signatures. The WAF is a last line of defense against automated scanning tools. It will not reliably stop a targeted evasive attack campaign. The reason SQL injection persists after 2 full decades of widespread awareness is a combination of legacy codebases written before prepared statements were standard practice, development time pressure that rewards whatever approach appears to work quickly, and the deceptive simplicity of string concatenation. The query runs. The test pass with valid inputs. The application behaves correctly for every legitimate user. The vulnerability is completely invisible until an attacker finds it, often years after the original code was written by a developer who may no longer be at the company. That is how SQL injection works. Thanks for watching.